Alrighty, so we're going to kick things off now. It's going to start with a short introduction before then we pass things over to Dr. Grace Douglas for a more in-depth seminar. So thank you all for joining today. This is a webinar as part of our Future Foods in Space Health Research webinar series. So this is the third webinar in this program. Like I mentioned, we're just going to go through a brief recap of the program, and then we're going to hand things over to Dr. Grace Douglas. So in brief recap, the goal of this Future Foods for Space program is really to help the future foods community, which can include, cell-based manufacturing, can include in other in situ production, but can also then include looking at novel ways to increase shelf life, stability of prepared foods and such, helping this community mobilize towards the space health domain, focusing on astronaut food challenges. So this is a collective effort with UC Davis and Tufts, along with funding by Trish. So we have several program elements that are listed on the right. To those who have been here before for the webinar series, this should already be familiar. For anybody who's new, welcome. Awesome to have you. So the webinar series, so we do have our first two webinars that were already completed. We have recorded them, and this webinar will also be recorded. So for those unable to attend, we'll be able to catch up on the recording. We will send out a PDF copy of this deck. And so you see there's these sort of blue, click here to watch webinar 1 or 2. That'll take you directly to it, as well as you can navigate it to them through our website. So this is the last webinar for our project year, and so we'll be in May refining for another series for you. With that, it's our honor and privilege to have Dr. Grace Douglas here to round out the year 1 for us. Grace serves as the lead scientist for NASA's Advanced Food Technology Research effort, and it is really such a pleasure to have her because her efforts and perspective here couldn't be a better guidestone for us in the future food community as we look to get into these advanced technology of food for space. So with that, I will stop sharing my screen, and I would invite Grace to take things over from here.
Thank you all for inviting me to speak here today. Okay, can everybody see my screen now?
Yes, we can.
All right, excellent. So I'm going to go through basically a history of the food, basically the food systems from the beginning of NASA's space flight through where we are today and the challenges that have occurred from that time. And a lot of the challenges that they faced in the past are still challenges today. A lot of the resource restrictions are still resource restrictions today. So the advancements in space food have actually remained in the realm of processed and prepackaged foods mostly because the resources are still very restricted. So I'm going to talk about that, and I'm going to talk about some of the things that we'd have to do if we were going to be able to advance, the challenges that would have to be solved to enable other food systems to come into that space. Okay. I cannot see my slides on the screen, so I can't tell if they are advancing. Are they advancing?
We now see food system gap focuses for Mars.
Great, as long as they're advancing. Okay, so when we're looking at space food research, we really look at 3 areas. We look at the food itself to make sure that the food is safe, nutritious, and highly acceptable in quality. And then we look at how it's impacting crew health and performance. So, are they consuming the system that we're providing? And is it providing them the level of health and performance through that mission that they're going to need in that specific concept of operation? So if it's a lot of EVAs or they're in microgravity a lot, we want to make sure that we are supporting the crew in those environments. But then in conflict with these first 2 is that the food has to fit within very limited resources. And unfortunately, as we move on to these Artemis missions and then on to Mars, this gets even more challenging. Okay. So the food system challenges that we've worked with in the past are continuing as we move into the future. Space, when we're in a spaceflight mission, it is a closed food system. So what we have sent into space is what we're going to have for that mission. We're not going to be able to really change that once we get there. And so that is a concern if you're growing something and you lose that and you're not able to provide an alternative at that point. Everything needs to have multi-year shelf stability. So especially if we're going to Mars, we need 5-year shelf stability. And right now that's at ambient temperature. So that ambient temperature can actually be a little bit higher. It could be 25 degrees. It might even be 30 degrees at some points. That's a really big challenge when you're looking at making sure that any substrate that we're going to be sending is going to maintain stability for the lengths that we need. Now we are looking at cold storage, and there's a lot of resource challenges with that. So I will talk about that a little bit later. But right now, our missions on the ISS do not have cold storage. Everything is just stored at the ambient temperature of the ISS. We are not able to cook. That introduces a lot more logistics and resource challenges. So right now it's just heating and adding water. Everything that we send has to limit crumbs, free liquid. They're not transferring foods in space. It really has to have a certain viscosity and surface tension to keep that food in the package or on the utensil so that they don't have a lot of debris in the air. And for that same reason, we cannot send glass. And all of our packaging is lightweight and flexible to try and meet the resource requirements. Crew do not have a lot of time to prepare food. Even on the ISS, they're often very busy. And so being able to consume a meal quickly, heat and add water, heat the food quickly becomes very important. And this is going to become even more important if they're on the moon or on the Mars surface and they're doing a lot of EVAs. Some of those days they might only have, maybe 2 30-minute meals around their EVAs, and they have to be able to get a lot of calories in quickly to maintain that high caloric usage rate that they'll be in with those high tempo EVAs. And then we really don't have a lot of water for these systems either. So we don't wash or reuse containers. Even with recycling water, they are restricted in water. Right now, for food and beverage use, they get 2.5 liters per day each. And that does increase with high intensity EVAs. So I'm not going to talk in detail about the history of the food systems, but the really important part is that it was always processed and prepackaged to date. And that a big reason for that is we can prove safety on the ground. So we're processing and packaging on the ground. We can prove safety on the ground. And then they also can consume it very easily in space flight and very limited time segments. So they don't have to cook. They don't have to prepare anything. They're basically just heating and adding water. So as we go through the history of the food systems, it's basically stayed that way. The advances have been we have improved upon the food. We've improved upon the packaging. We've increased the variety of foods, which has really helped with consumption. But I also want to talk a little bit about the transition of shuttle to International Space Station because there were some interesting things there. So shuttle had, by the time we were doing shuttle flights, we had about 130 different foods. We had this lightweight packaging system. Those were 2-week missions. The food launched with the crew. When we moved to International Space Station flights, the crew was still getting about the 130 foods. They were still getting preference menus. So we did work with the crew members to provide them a nutritionally balanced meal, but with foods that they chose. And when we went to International Space Station, rather than the food launching with the crew, it would be launched on resupply vehicles that did not always launch on time. And so with those launch delays, there could also be crew changes. You could end up with crew eating someone else's selections, which can end up being very challenging. If somebody really likes something and somebody else doesn't, but then they have to eat that person's food, that can be challenging with intake. So what we do know is even with high performing individuals, food becomes more important in spaceflight. So if you really have to eat foods that that are not high on your list of foods to eat, you are likely to eat less of those. Your intake's going to be reduced, and that can have other impacts. So for the International Space Station, those impacts could be bone and muscle loss, cardiovascular deconditioning, and ultimately over time you could end up having health and performance impacts. And so that's what we start becoming concerned about, all of those things. So for ISS, we did end up changing to a standard menu so that most of the food was sent up like pantry style in these categories, and the crew would share those. And then we did increase the variety as well to about 200 different items. And we also worked to reduce the sodium because sodium in processed foods ended up being very high. We used to use a lot more commercial foods. We started developing a lot more of our own to reduce that sodium in the processed foods. So our processed foods are made specifically with nutrition in mind. Um, and then we do still provide some preference foods. We're able to provide some preference foods that we can usually get to coincide with the crew, with the right crew members that are up there with the resupply vehicles. And so they get about 75% of their foods from standard and about 25% from preference. We do know that preference food is very important to them. Having variety, choices amongst the food is very important to get their nutritional intake. And on ISS, they still are limited to hot metered water and ambient metered water. The only way that they can chill any food is that they do now have a small chiller for food that was not always there for ISS. And they can chill some food or beverages and some condiments. And then they have a food warmer. And that's it for preparation on the International Space Station. And this is actually going to get more challenging as we move to Artemis. And even right now for the ascent and descent to the International Space Station, they have no ability to rehydrate or heat foods, so they just eat um, ready to eat foods at ambient temperature, and they can only just drink water. There's also a food mass limit for those. So again, everything is just very resource restricted. When we're looking at developing foods for space flight, we try and look across our whole food system and determine where we might be able to add variety in nutritional balance. So we're looking at it from a whole food system perspective. Our goal is to be able to provide foods that most people would want to eat and provide foods that give choices within nutritional areas. So everyone will have different foods that they are going to enjoy more than others. And at the same time, though, we really have to make sure that most people want to eat those. So if you're thinking vegetarian and vegans, it's still about 10% of the population. So our food, it have a good portion of meat items. We're not able to support allergens or um, food restrictions because we are mass limited, and we do have to support most people. And so, which allergens would you even target at that point? If you target all of them, you really don't have a lot of food choices left. So, there's a lot of restrictions and those kinds of things when we're working within these systems. But when we're doing the development, we do have fat and sodium limits. Where we try to keep it within mass and volume constraints. We try to target at least a 2 to 3 year shelf life for the International Space Station. And we do sensor evaluation at multiple time points to make sure we're meeting that requirement that it's generally going to be acceptable. And then, so this just shows the food preparation on the International Space Station that I'd mentioned, the water dispenser, and then the small chiller and the food warmer. But food, again, is very, very important to our crew. They do celebrate around it like we do. They do find variety and choice very, very important, and being able to have familiar foods very, very important. And also that preference is very, very important. And this also might not be available at the level it is on the International Space Station as we go forward on these Artemis and International Space Station missions where we're sending food ahead. It's very mass limited. And the missions are very specific. So even when we go to Mars, we might have to send food well in advance of crew. So a lot of these foods, we don't ask them to take these pictures. This is just to show how important this is to them. They take these pictures around food because of how excited they are when they get some of these deliveries. And unfortunately, we're just not going to be able to have some of these things like the fresh produce or these pizza kits, which have a very short shelf life, and they get sent occasionally when there's super late loads. So if we can put something on a resupply vehicle the day before it launches, we can put some produce or something like a pizza kit on there, and then it has a very short shelf life, but it gets there in like a day. So we do learn a lot from the International Space Station. So we have learned that the immune system can be dysregulated. We do still see body mass loss and muscle loss. And we do see, we'll see increases in stress on the International Space Station. So we see impacts to physiology. And we do understand that the diet that we're providing them is going to have impacts to that physiology. And that's going to become very important to health and performance, especially as we get further away from Earth. Our medical capabilities and return to Earth capability become more limited, and our resources may even become more limited. So we're going to have to provide a food system. How can we provide a food system that in itself can maybe be a countermeasure? So that's going to impact our microbiomes and basically every system in our body from that food system that we provide and the choices that that crew is making. So that's what we've really been trying to focus on. How do we make this better for them? How do we make it so that maybe during these challenging phases they can consume the calories they're going to need to perform, even if they have limited times to prepare or consume food. So our challenges as we go forward, I'd mentioned, are on Artemis are going to increase. So Artemis, actually, we had to cut our food mass by 10%. We worked within our system to be able to achieve that for the upcoming Artemis missions. And we are also looking at some higher calorie foods for some of the missions for HLS, or the Human Lunar Lander, as well, because they will not have as much time to consume food. So when we go to Mars, it's going to get even more challenging. So we're looking at possibly as long as a 3-year mission. And if we send food in advance and we don't have a refrigerator or freezer, we would actually need about a 5-year shelf life at ambient temperature. We know that that's a huge challenge for the prepackaged food system. So again, I will talk a little bit about refrigeration. But in addition to that, they might not have even selected crew at the time the food launches. And that is a scenario. There's different ones, but there is a scenario where we might be sending food well in advance. So right now, there's no precedent for a 5-year shelf life. So if we look through history, food has been a deciding factor on whether a lot of exploration has been successful. The age of sail, more sailors died of scurvy than all other causes combined. And while we understand vitamin C today, vitamin C is very labile. And so on a 5-year mission, it is a big concern for us to be able to provide that. Antarctic missions, they had cold storage, but they still often had challenges with food. They were also able to hunt, but they often still had food shortages, food challenges over time because things went wrong in the missions. And food was one of the number one reasons that those missions weren't successful, or it was loss of mission or loss of life. And even the modern US military, they try to limit use of the meals ready to eat or the prepackaged foods to 21 days. And then they try to actually provide better meal services for soldiers in the field, bring them back in, get hot foods out to them, because they know that from the studies that they've done, that they will start seeing performance impacts if they provide MREs for too long. So we do get the question, why can't we just provide, something like a new vitamin or some sort of supplements? So we really need them to get the calories, and the nutrition and the quality are both going to decrease. We really need to provide that high quality food system that has that nutrition in it, so they're getting the calories and all the macronutrients they need, as well as the micronutrients. And they do. We know that that choice, that acceptability, is very important to them. So you could end up, if it really is a supplement, you could end up with clients' concerns. The nutrition will also decrease in the supplements. We've seen that. And so the best way to provide this is really through a food system that they want to eat. So we do know again that our prepackaged foods do have those limitations of nutritional degradation over time, the quality degradation over time. It is a high mass and volume system. We really haven't seen full mass analysis on any other system because there's no other spaceflight ready system, but there's a lot that goes into any system. So if you're trying to grow something in flight, there's going to be the mass of all the equipment you have to take, the mass of the supplements you have to take. If you are using water and trying to recycle water, how is that affecting the water recycling system and their consumables that they have to replace certain things in that system? And is it putting off volatiles into the air? So there's a lot that goes into that, including crew time. Crew time is considered a very valuable resource. How are you cleaning that system? What are the cleaners that you need? That is a huge gap with every system that we really don't have with the prepackaged food systems. So these are actually the requirements for all food systems that they have to consider. So nutrition is just one. It has to be something that the crew finds very usable, that they want to use. So if you're thinking of exploration missions, which we're currently doing, exploration missions that we're going to be doing for some time, rather than missions where we might start having a settlement, more people, specialists. Um, you, it's more of a thought of what do you want to do when you come home at the end of a really busy day? Do you want to just, be able to cook something really fast and easy that's very familiar and comforting and delicious? Or, we don't have bioreactors in our own kitchens, right? So that's where the challenges come in. How would you make a system be something that produces variety and choice and is something that you would want to use when you came home at the end of the day? And that would be the kind of thing that could potentially be used on an exploration mission. It also has to be reliable. So we don't want to have the chance of food loss. We have to make sure that that food's there for the crew. We have to fit within the resources that are available. It has to be safe, and again, that is a huge challenge. How do you clean these systems in spaceflight when the water system isn't compatible with most of the harsher chemicals that we use to make our system safe on Earth, that we use to clean our systems? We use a lot of water and very harsh chemicals to clean our systems. And right now, that's not an option in flight. Testing is also not an option in flight. We don't have a microbiological lab with us. The test capabilities that are out there for fast and rapid testing, they're at a level where you might be able to do some quick environmental sampling or maybe even water sampling. But food is another challenge because you have to get a certain amount of that food, and then you have to usually do an enrichment step to be able to tell what's actually in that. So we really need something game changing on how to make sure that these are safe, how to clean systems in these very resource limited environments. And then, of course, you have to provide that variety. So any system would need to be able to basically provide that, 200 plus choice variety, even for something like a 6 month mission, and really more than that as you get longer. Um, Okay, so this is just a concept. So NASA uses roadmaps to figure out how they're going to advance, and this concept just shows kind of the ideas that would have to be figured out if we're going to get to Mars. And so we do a lot of testing within prepackaged food systems right now. So again, this is research on the food, the resources, and the human to make sure that their health and performance is maintained. And then for crops, there's quite a bit of work going on in crops as well. Crops is the most advanced system, and it is a highly familiar and highly acceptable system to crew. And then we do have the other bioregenerative systems on the roadmap as well. There's a lot more challenges with a lot of those systems if you were going to get to Mars. So right now, the prepackaged food system really still is the focal point because we can confirm safety prior to launch. It doesn't take a lot of infrastructure or crew time, and we don't have risk of food scarcity once we send it. So we are working on ways to get to that 5 year shelf life, and that can include combinations of how do you formulate, process, package, and then store. And storage is a big one. So do we get to 5 years if we have refrigerated or frozen storage? And For some foods you can, and then we find for some foods you can actually still get there with 21 degrees, and then for some you might need frozen, and for some foods you might not even get there. We've done some testing across our system. We're trying to do some more because foods vary very much from food to food. It's You really can't extrapolate, so that part is hard. And there are some nutrients that are still pretty labile, so we're still looking at that. But ultimately, cold storage will definitely get you a lot further on that roadmap to Mars. And so this just gives it kind of an example of some of the data from some of the studies that we've done. So this is apricot cobbler at 5 years. The vitamin C is gone if it's stored at 21. It's maintained pretty much fully stable if you keep it at frozen temperatures. You do lose some at refrigerated temperatures, but if you look at it, both refrigerated and frozen actually look pretty good. So it's just, are we willing to take this much loss? And so we have to look across our food system, look at our other foods to really understand that. And this goes back to food system inputs as well. If you're looking at other systems, what's their stability under different temperature or environmental conditions? So when we look at refrigeration, though, it is a huge resource hit. We are looking at a little closer starting right now to see how we would implement refrigeration on these missions because we are going to need it. So that is actually a huge gap too. How do we get the most efficient refrigeration? Active refrigeration does require a lot of a pretty big mass hit. And it's about 400 kilograms for every 1,000 kilograms of food. And we probably would need to, for a 3-year Mars mission, refrigerate something like 5 or 6,000 kilograms of food at least. So if we look at passive refrigeration, there's just a lot more unknowns with passive refrigeration right now. Space isn't always cold. It really depends on the orientation of the vehicle. If it's oriented towards the sun, it could get very hot. So you need things like solar shields. So there, it really needs a full engineering feasibility assessment compared to active refrigeration to understand this further. And then for human performance evaluations, we have done and are doing evaluations across multiple analogs here on Earth. That gives us a lot of information. We would love to do all of our evaluations in spaceflight because we also have microgravity and radiation and the higher stress. However, these ground analogs give us a lot of really good information. You can get an entire complement who's going into that habitat to basically be in the same experimental design, which really does help with data collection. We can also set things up to be exactly like the mission we're planning for. Rather than on ISS, they're going to be doing all kinds of things, maintenance for ISS. So if we want to mimic something like a lunar surface mission, they do some testing in this 20-foot atmospheric chamber for multiple days. If we want to do Mars assessment, we actually set up this analog crew health and performance exploration analog. They just finished a 378-day mission this past summer, and that was set up to be very much more like a Mars surface mission where they were doing high tempo EVAs and they had a major time delay the whole time. So they had that long isolation and confinement, and a lot of their resources were restricted. It was set up to be very integrated to really start understanding that resource impact on human health and performance, to get some cognitive and physiological and physical data in relation to those resource inputs that we don't have a lot of that information actually right now. So we're going to get a lot of good information that's very integrated from this evaluation. That information is really necessary when we're working with programs and they say, well, what's your impact if we remove this resource? And if you have data that shows any sort of cognitive decrement or physical decrement over time from limiting resources, that becomes very important when you're trying to make those resource risk decisions. So the other thing that we have in that crew health and performance exploration analog study is we do have crops during certain segments. And that becomes important because as we move towards the Mars missions and they are not going to get the resupply with the fresh produce that they get right now every couple of months. And yes, it's not a large amount of fresh produce, but it is important. It can make a difference. How important do crops become? Because right now, to send any crop infrastructure, it's going to be a resource hit. So how important is that to crew health and performance? And so we're going to be able to start getting that data in relation to not having it throughout the mission design here. So I did also mention that we can do some evaluations in this atmospheric chamber that have been very helpful when they're running tests to look at lunar surface EVAs. That's been very important because they do have less time to eat when they're running those evaluations as well. And we have evaluated some food systems that have some higher calorie meals mixed in, because the goal ultimately is if you provide a higher calorie meal in a resource limited environment, you are taking away other food items that are individual. So it might be easier to eat the high calorie meal, but are they going to eat those high calorie meals when their choices are more limited? Those trades can become important. So our ultimate goal is to try and define what is the best food system to provide for most people, that most people are going to get the most calorie and nutritional intake from. What works the best when you're in these environments, because ultimately you can provide the food, but if they don't eat it, they're not going to get that benefit. And then we really do want to keep looking at bioregenerative foods. Right, the crops again are the most the highest TRL level or technology readiness level, and they're also considered highly acceptable by our crews. So that psychological appeal, that fresh food appeal, and also just as we do get to more mission self-reliance, as we move towards Mars and possibly having humans live more permanently there, we need to start looking at what does it take to have these bioregenerative systems. But really, where is that trade between a break-even point? Where does it make more sense to start having more of these other systems than prepackaged foods? So, right now in our own lives, we often have a mix of prepackaged and cooking. But ultimately, where might we start having, enough people on another planet too, that they also have very specific tasks, like you might have food specialists or something like that. If you're on an exploration mission, you know, are those explorers going to have time or want to do those tasks around food? So that's a consideration when we start going into this as well. So we do know that crops, again, the crew really likes these, similar to the other foods. When they do get to have crops, they tend to take a lot of pictures around them. So we know that they really enjoy these. They're very important. But right now, we do still have that risk of food scarcity. And we also have the microbiological risk, which is uh, we need something game changing. So right now, that is a huge gap to having any bioregenerative system on actually producing food for a spaceflight mission. And then that crew time requirement is another gap in getting that kind of infrastructure in place just to even start showing that this is the direction that we should be going in. Okay, so this just shows we did publish a paper on our current crop roadmap, which kind of goes through what I'd mentioned. It's expected that we would start with some pick and eat. You start showing some ability to do that. We start working towards it. And then as you can show more reliance on the systems we have in place, you have more food specialists in place, you can start increasing reliance on those systems. And ultimately, we have to avoid any chance of food scarcity. So for the future food system, there could be a lot of different things that come up a lot in these conversations, like subcultured meat, insects, algae. Um, it's possible any of these things or all of them could end up in a future food system, but right now there's a lot of challenges with these that would have to be solved to even start looking at them in a future food system. So ultimately, especially right now, the question is, what are we willing to do in our own kitchens at home? And for any of these exploration missions, that's probably going to be the limitation. It has to be safe, easy to clean, easy to use, and something we want to do after we've worked all day and get home and just want to eat something that's familiar and comforting. So that was my last slide. We do work with a lot of different teams uh, at NASA to make the research that we're working on happen. And then there are, of course, a lot of other teams that are working on NASA research to help with these too. So I'm happy to take any questions.
Fantastic. Thank you so much, Grace. Really, really fantastic talk. I learned a lot. I'd recommend folks put their questions into the Q&A chat box, and I will kick off with a question of my own. I think as I was listening to you speak, it seems like you're often pulled in a lot of directions with different mission architectures. And so I'm wondering if there's any tips or useful ways of thinking about how to balance those different spaces and constraints, and if there's any particular challenges that would be useful for the community to know about there.
So when you say different architectures, are you thinking like water restrictions, and can you just expand?
Yeah, yeah. So I guess I'm thinking of okay, if we're talking about Mars, but then we're also talking about ISS or the moon, and so very different durations, which then might
Mhm,
have different constraints, like maybe water usage,
mhm.
perhaps. Um, I'd love to see, even which constraints are important to be thinking about in those, right?
Well, I would say all of them and all of them. And I'm not kidding when I say that. I don't think it's going to get better when we go to Mars, especially for the first missions. I think, based on the work that I've done with Artemis, even, it's getting more restrictive. And Mars is further away. Um, and we're going to have to send a lot more resources when we go. So it is going to be limited. And water is going to be restricted, mass, power, everything will be restricted. And I think it's just actually going to become more challenging, not easier. So I think the biggest things to think about are all of those things are restricted. So how do you minimize your use of them compared to Earth? Second, how do you game change that microbiological issue and the cleaning issue if you're doing something in the bioregenerative space? Because that is a limitation that remains, that has it never really there's a lot of work going on across different teams, and I never really see anybody work on that problem. um, Water is going to be limited. We're not going to be able to use the harsh chemicals. We don't have a microbiological lab. Those are the things that we depend on to keep us safe here on Earth, and it's going to be much worse if they get sick in space. So how do we basically work to solve that issue?
Hmm. Thanks.
And UV light is not the answer.
I have to admit I'm guilty that in my head popped up some recent UV light sterilization innovations. So I've given myself a slap on the wrist for that. I'm going to be slightly greedy, and before we get to the rest of the Q&A chat, I did want to have one. I do have one other question for you, if it's okay, which is really, shift as you're shifting to food as a countermeasure. Like how to integrate that with the whole system seems like a lot, and but also a real benefit. I'm curious about how much you engage with the food as medicine community on Earth, or sort of where that stands in that transition in thinking of food as a countermeasure.
Right. So, what I would say is that we work a lot with our human health and performance science colleagues in operational designs and assessments here at the Johnson Space Center. So, even with that crew health and performance exploration analog, we set it up to be very integrated and operational. We're getting a lot of those performance metrics in relation to those resource restrictions. So, if our food system is more restricted, can we design it so that they're getting the nutrition they need, and that they're performing at the cognitive and physical levels that we need them to within those restrictions? And then you can always ask the question, can you restrict it more beyond that? But I think the we do work very closely with our colleagues, and that's probably the hardest part, because integrated studies are really necessary to understand the whole picture. You really are looking at the whole food system. It's not a single food solution. You're never going to get everyone to eat a single food. So we try again to have uh, a good variety in the system that provides a variety of nutrition, and that we can evaluate how well that's working across different teams in analog environments, and that there's other teams collecting that health and performance data, because that all becomes very important to really provide an informed strategy to the programs when they're making these decisions on that resource, you know, cutting resources here or providing more of them here. So
Great, thank you. And I'm really excited for when the results come out from the, I'm sorry if I'm pronouncing the Chapia study that you were teeing up there. Seems really interesting for a lot of what you're talking about. So I am going to move to a couple questions that are in the chat. So the first question is, what is the role of robotics for crop production? And I would say generalize that to food systems in general. So the role of automation, and do you see that as essential for longer duration missions or optional?
so I would say it's definitely in the space of trades. Right now, I think there's a lot of challenges even with robotics. There's not a robotic system right now that I've seen, that would be able to support a space mission and produce the foods for crops or really any other bioregenerative system. They're not developed at this point, right? So again, very low technology readiness to support any sort of near-term mission. And then you're going to also have the resources, the robotics. So, what kinds of spares do you need for the robotics? Are they really robust and resilient? Can they handle water? So there's a lot of questions that come up with robotics. Do you need somebody who can fix the robotics? How often are they going to break? How much crew time does that take? Right. So robotics does, you know, it can make life a lot easier, but it has to be a super resilient and robust system, and then also fit within that mass and volume trade to, and power trade. If it uses a lot of power, that can be a challenge to enable these missions. Again, it really comes down to that trade, and we've never seen a lot of these other systems do an actual full trade because they're not developed enough to even do that. What is the true cost of these systems? You can't really just look at the mass, you have to look at the whole piece, right? You're going to have to send this much of all of your stuff. It has this kind of shelf life and this kind of need. It's going to put off this into the environment. It's going to use this much water, which is going to impact your consumables on the water system, and impact your consumables on the air system, and what's your crew time usage, and what kind of chemicals are you needing to clean it, and is that compatible. So that's all in that trade. And then how much produce are you getting out of that at the end, and what kind of variety is in it, nutrition is in it, and is that going to meet the acceptability requirements of the crew? So there's a lot in that trade space. And again, I haven't ever seen a full assessment, even on crops, that is actually a full assessment.
Great, thank you. And it has me wondering too, like, are we taking away the benefit of people getting to like nurture a little crop by fully automating it? I don't know. Okay.
Yeah, that's definitely one of the questions too.
Yeah, I mean, I know I love my little houseplants despite how bad I am with them. So we'll switch gears just for a second to ask a more, I guess, people who want to get involved from here who are excited about, what calls from NASA or other places would you recommend for people to get engaged and sort of with this food research? So any grant opportunities upcoming or specific programs to keep in mind? And
So I would just say to watch the Inspires grant calls. I don't actually do grant calls. Those would be the program. So it would be like space biology probably does more stuff in the bioregenerative area. And then, the human research program does definitely does work with food. So I would just say it would be watching what comes out in the Inspires grant system from NASA.
okay, perfect. And as far as the HRP colleagues, in a recent conversation with one, it seemed like the omnibus that comes out might be a reasonable place for folks who want to start something small as well. Okay, so I do want to then transition us back to science and technology. And so I'm going to read this question verbatim. I read that water content of prepackaged foods for Mars needs to be reduced to less than 30%, instead of higher content currently included in ISS due to advances in life support systems that are more efficient in oxygen recovery. Is this the case? So we need to use this as a design criteria?
So yeah, that would be one of the things that they are trying to look at is, our prepackaged food system right now. So this was an ISIS paper that came out. So I'm assuming somebody read that. We had 46% water if we look across our ISS food system right now. And a lot of that does include things like ready to eat, like meals ready to eat, right? They're not, we have our own because they're lower in sodium, but they're basically, packaged in foil packages, flexible foil packages, so it's canned food and pouched, and they don't have to add water to those. They can just eat them. So it provides, more variety. If you just have freeze dried foods, that's less variety. But the if they close the water loop, so right now the water loop's not actually closed on ISS, they just do recycle a lot of the water on ISS, but they are expecting new water to come into that. And water from the food is part of that new water. So they're eating the food, they're getting water from the food, and that comes into that recycling system. So if they close that water loop further and we don't reduce the water in the food, then they would just end up with excess water. So if they close the water loop further, that takes technological development to do that, and we do reduce the water in the food, then that can end up in a mass savings in the food system because we won't be bringing that water in the food system. So that is one of the things that they are looking at from that perspective. But that is from the perspective of we're bringing the water in the food system. So if you have a bioregenerative system and you're planning on using the water from the recycling system, it would definitely be different. There's still limited water that's going to come from the recycling system, right? So those are still considerations. Water is likely to continue to be limited, but as far as reducing water we're bringing in the food system, that's where that comes from. I hope that answered that question.
I think so. And if not, we can get a follow-up question. Um, so switching gears a little bit to one of you said you need a game changer in how we approach the microbial risk. And so the question here is sort of what are the challenges or possibilities about probiotics or fermented food into these more space environments because microbes are so restricted? Is this being researched? And so to me, I think there's an underlying question about sort of do you keep it totally free of microbes in the environment, or do you also use some of this to help nudge the microbiome or the space into a certain direction?
So I will say that those first requirements come more from the program and the flight surgeons. As far as our food system, we are required to meet those microbiological requirements, which are restrictive. We are not able to fly fermented products for the restriction reasons, and we've had these discussions. So when you look at fermented products, there's a history of safe use. You have a lot of microorganisms in them that would technically outcompete, and a lot of the bad stuff, right? We don't really see a lot of illness happening from eating those products, but it's very challenging to test to see if there actually is any pathogen in a fermented product because there's so many other microorganisms in it. So a lot of the products that are available are not actually tested for pathogens. There's just a safe history of use. They have, the good bacteria in them. But that has always been a limitation because when we go to spaceflight, we do know that from the data that's out there, they can go through immune dysregulation. What exactly does that mean? And then the flight doctors will make requirements on what we're able to provide and able to do. And so right now, we do not provide fermented products in the food system for reasons like this. And that's a much bigger discussion that would go well beyond the food system. There are teams that I believe are looking at things like microbiome and different, how do you use the microbiome in effective ways? That is a question that does come up. I haven't seen anything operational come out of it. So I think how do you take that to operation is still a gap, right? How would you use that operationally? Like, what is the data actually telling us? And I haven't seen anything conclusive come out of that. But if anybody knows of anything, I'd be interested.
Great. I hope you get some follow-up on that. And And to me, I almost think about prebiotics as well. So like that being maybe the safer place to start without introducing actual microbes, but just food for the microbes that we know we want to keep around. Um,
So I think we do have that actually. So a lot of
oh,
prebiotics is just fruits and vegetables, right? So when they market prebiotics, it's to the people I feel like who don't like to eat a lot of fruits and vegetables. So we do have a lot of fruits and vegetables that are processed, but still have all the health benefits in our system.
awesome. Um, okay, and now we have a question here. It might take me a second to digest it. So it looks like a lot of the challenges here in the food systems require us to start to think holistically about solutions. And those solutions that might have parallels on Earth, but not be exactly what you're facing. So the follow-up there is, as we're looking at those parallels, are there multidisciplinary teams that you might be assembling or working with across humans, plants, and microbes, maybe taking from the systems that we might be trying to move towards on Earth as well? I know that you already,
So
sorry.
if you're looking across humans, microbes, and plants, I don't think we're doing anything specifically like that. I think it's more in the food safety realm that we look at things like that because we do have, safety evaluations done in relation to plants in the human environment, right? I don't know if that answers the question, but
Yeah, I think food safety being a place where you have this convergence of different expertise makes a lot of sense. Um, okay, and I think with that we've run through our questions. Unless anybody sneaks one in last second, uh, I'd just like to say thank you again, Grace, for your time. This has been really informative, and I know the whole community here, and when we post it that weren't able to attend, will already do or will really appreciate this as well. So with that, thank you everybody for showing up today. Um, Grace did put out her email address. You're always welcome to send me a message as well. Until next time. So cheers.
thank you, everyone.